All right, yesterday we went through and did calculations related to a strong acid, strong base titration, which is the easy type of calculation. I don't know if you thought those were easy, but essentially what we need to understand is, first of all, when we do a strong acid, strong base titration, what's really in the mixture is either H3O plus from the acid or OH minus from the base, right? It says in part I1, or II, of your outline, for a strong acid, strong base titration, strong acid plus strong base, what is the reaction that's occurring? You guys see what I'm looking on the outline? The neutralization reaction. Find it? What's it say?
For a mixture of a strong acid with strong base, the neutralization reaction is H3O plus OH minus equals to H2O. The K for this reaction is 10 to the 14th at 25 degrees Celsius, so the reaction goes to confusion. This allows the pH of mixtures of strong acids and bases to be determined from the limiting reactant, either the acid or the base.
So that's exactly what we talked about yesterday. When we figure out, based on the volumes and molarities of these things that we worked with, we're either going to have excess H3O plus in solution, or we're going to have excess OH minus in solution. Right? So all we have to do is figure out how many moles of each of these we have, and then do an excess reactant problem. If we have excess moles of H3O plus, we just figure out how many moles are left over after this reaction occurs. We divide by the new volume of solution. That gives us the molarity of H3O plus. And then if we take the negative log of that, it gives us the pH. If, on the other hand, we have more moles of OH minus is going to be in excess. We figure out how many moles of OH minus are excess. We take the negative, we divide by the new volume. We find the concentration of OH minus, and then if we take the negative log of that, we get POH. Well, we just take 14 minus the POH. That gives us the pH. Question?
Okay, so I get that you have to do that equation with H3O plus and OH minus, but like, let's say you had NaOH and then HCl. Like, what happens with the Na and Cl ions? Like, I know when we did like net ionic, we crossed them off and stuff like that, but what really happens to them in a solution? Like, why aren't we worried about like other ions?
Well, what do we know about strong acids?
They completely, split up. Completely give all their H's.
Why?
Because they're strong.
That seems circular.
What does that tell you about Cl minus? That every time I take an HCl molecule and put it into water, water grabs onto the H plus. Tells you that, Sidra? Cl minus has a very weak bond to that H plus, right?
So they're strong acids that have weak bonds?
They're strong acids because their conjugate bases, in that case Cl minus, is terrible at grabbing onto protons. That kind of begs the question, how do you get it to grab onto that proton in the first place? How do you actually make HCl in the first place? Okay, let's not worry about that right now. The point is that if we have HCl, Cl is so bad at holding onto that H, every HCl molecule is going to give up its H, and so all we really have to worry about is the H3O plus. Okay, the Cl minus, if it bumps into a water molecule, what's it going to do? Nothing, because Cl minus is worse at grabbing onto protons than water is. The conjugate base of a strong acid is a weaker base than water. Okay, if you think about it, water, we saw when we did that simulation, the autoionization of water. This is water acting like an acid and a base. Would you agree? One water is accepting a proton, the other water is donating a proton. So this is really like water's acid reaction, but it's also water's base reaction. What's the K for this reaction?
10 times.
10 to the negative 14th. Okay, so we call that Kw, but really you could call that the Ka for water, or you could call it the Kb for water. Okay, so we're talking about acids and bases. We want to compare their strengths to the strength of water. Anything that has a K value higher than 10 to the minus 14th is a stronger acid than water. Or if it's a base, and its Kb is bigger than 10 to the minus 14th, it's a stronger base than water, right? HCl, on the other hand, this reaction here has a K value of something much larger than 1, maybe 1,000,000. I'll just say it's 1,000,000. Ka here is 1,000,000. Strong acids should have a K value larger than 1 because it's product favored. They completely donate that proton to water. Okay? Remember, we're learning that equation. What's the relationship between a Ka for an acid and the Kb for its conjugate base?
They're like inverse of each other.
It's like 10 to the negative.
Oh yeah.
Find that on your equation sheet right now. As we work through these problems, I want you to be continuously going back and looking at that equation sheet and looking for it, because there's no way you're going to remember all these K equations and H3O plus and logs and all this stuff. So we need to really get good at finding it exactly where it is on our equation sheet, so when we need it on the test, we don't have to be hunting for it. Okay? So what this equation really says, well, Kw is a constant, yeah? It's always 10 to the minus 14 at 25 Celsius. But what this means is that as Ka goes up, Kb goes down. The stronger the acid, the weaker its conjugate base. The weaker the acid, the stronger its conjugate base. Okay? Well, if HCl has a Ka of 10 to the 6th, what would Kb be? What would be the value of Kb? Ten to the what? No, Kw is 10 to the minus 14th. So what can we multiply by 10 to the 6th to get 10 to the minus 14th?
1 to the negative 20.
10 to the negative 20th.
Or
Cl minus
maybe 10 to the
theoretically
negative
could act as a base, since all reactions are reversible, right? But its K value is 10 to the minus 20th. So if I have Cl minus and I put it in water, theoretically it can grab protons off of water. But it does so infrequently. K is 10 to the minus 20th, that actually water is a stronger base than Cl minus. Water can do that with a K value of 10 to the minus 14. Cl can only do it with 10 to the minus 20th. So for all practical purposes, we can ignore whatever Cl minus is doing because water is such a stronger base than Cl minus. Okay? So in answer to your original question, nothing really. What do Na plus and Cl minus do in this reaction? Nothing. Because they are such weak conjugates that water does more than they do. Okay? We'll call them Kranskis. Okay, so what I did up here, and I'm going to share this with you guys at some point, is I basically used one of my best friends.
13?
4?
No, we got like
7? No.
I can check the list.
Better check. I think it's up there. Okay, so basically what I did is say, all right, what amount of milliliters are we titrating? That's what I plug in here. What is the concentration of the acid that we're titrating? What's the concentration of the base that we're titrating it with? I have a K value here, which I don't really need because it's a strong acid, strong base. Okay? And then what this thing does is for various amounts of milliliters added, this is not 0.05 anymore. This is just the NaOH. That's 0.1 molar here, okay?
Especially
So-
for number 4.
Number 4, I told you, they're up there. It's so useful.
7 is Wikipedia.
Yes, yes. Okay, so what it does, here's the milliliters added, right? Which is what you're going to have to use during this titration. They're going to say, okay, if I titrate some amount of an acid with this concentration with a base that has this other concentration, tell me what the pH is for a certain number of milliliters added. Okay, so I did it for all the different possible, not all of them, but all the integer milliliters added. Okay, so what does it do? Well, first what it does is it says, all right, well, let's look at how many moles of acid we have. So I multiply these two together. The equation's way up on top. A6 times A4. So I'm multiplying the volume of this times the concentration of that. That's giving me moles. Actually, it's giving me millimoles. Let's make this. Well, no, I guess because I'm using milliliters here. Okay. It's essentially giving me the moles of acid, right? Then I'm subtracting from that the milliliters of NaOH added times its concentration. So that's how many moles of base there are. So I'm saying how many moles of acid are there, subtract the amount of base that you added, that's going to tell you how many moles of acid are left, right? Then I divide that by the total volume of the solution, and that gives me the new concentration of my acid. Okay, so what you can see here is the acid concentration goes down, down, down as we add more and more and more NaOH. Well, at a certain point, it's going to go below zero. Right here. Is that possible? Not really. What does that mean if my acid concentration is going below zero?
Like a really basic.
It means that at this point here, I've actually used up all my acid, right? These calculations are meaningless right now. We can't have a negative concentration, okay? But all the way up to this point, at 100 here, that's the equivalence point. We've added exactly the right number of moles of OH minus to react with all of the H3O plus that we originally had. Does 100 milliliters make sense for the values that I put on top? We had 50 milliliters of acid at 0.2 molar. We're adding 0.1 molar, so it should take twice the volume to have the same number of moles, right? So that makes sense, okay? So what I'm doing then to calculate the pH here, I got a big nasty if-then statement. You guys know what those are? Basically what I tell the spreadsheet to do, come on, you can make it, get up there. Why is it so hard? I say, if this number is greater than 0. If this number is greater than 0, we have excess acid. If there's excess acid, all I got to do is figure out its concentration and take the negative log of it, right? So that's what it is.
Oh.
That's my bat. Okay. So, if I still have excess acid, I just take the negative log of that, and that will give me the pH. Right? But, if my acid concentration is not greater than 0, that means I have excess hydroxide. So I had to make another column here to calculate how much hydroxide is in there. Okay, so it's all zeros here. Why?
It's all used up.
It's all used up. It's a limiting reactant until we get to at least those 100 milliliters, right? So this thing basically says, oh, it's nasty. Basically, it figures out, okay, if I have some moles of this, how many moles of base did I add? If there's any extra, tell me what the concentration is. Notice it doesn't give values until we get to past 100. We don't have any extra OH minus in solution until we've added more moles of OH minus than we had of H3O plus in there originally. Okay? So now these numbers are going up, and basically what my pH calculator does is to say, if we have some of this, take the negative log and that's your pH. But if we don't, take the negative log of that, that's your POH, do 14 minus the POH, that'll give you the pH. Okay? So for strong acid, strong base, all you're trying to do is figure out who's in excess. If you figure out how many moles of excess there are and divide by the total volume, it'll give you either the concentration of H3O plus or the concentration of OH minus. And you should be able to find the pH from that. If this is excess, it's real easy, negative log it. If this is excess, negative log it, and do 14 minus that. Does that make sense? If it doesn't, you've got some work to do. Okay? And I guarantee it won't make sense to some of you. This is probably the second time you've actually thought about this. Do some reading. Watch some videos. Go to the Lit Center. Okay? But you will have to do this, I guarantee it. Okay? Moving on to the much harder. Some of you are saying, I don't understand that. Well, you'll get there eventually. In a weak acid strong base titration, we've got a little bit harder job to do. Oh, by the way, just show you the graph. Pretty much what we came up with. See that? Pretty much what we came up with yesterday, right? Okay, so the pH stays low, 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 low. Remember when I was actually doing it, and it was just pink, 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 and then all of a sudden we got all kinds of crazy colors, right? And we were adding just a few drops, and the color was changing like crazy. Okay, so this is the theoretical curve for amount of NaOH added versus the pH. Although I do have one issue with my spreadsheet. There's one point it didn't calculate correctly. The one at 100, what's that called? No, what is
The intercept?
the equivalence point? The equivalence point. This thing is not correctly calculating the pH when I've added exactly the same number of moles of H plus and moles of OH minus. Why can't it do it? Because it thinks these are both 0. How can you take the negative log of 0? You could try, Lindsay. Error. There is no number that you can make the exponent of 10 that will give you 0. Maybe negative infinity, but that's not really a number, right? It's a concept. Okay? So, what is the pH at the equivalence point? 7. Why? What we always have to think about is, what's the strongest acid or base in solution? The strongest acid or base that's in our mixture will control the pH. If we have excess H3O+, that's the strongest for sure acid in there, that's going to determine what the pH is. If we have excess OH-, that's a strong base, that's going to determine the pH. But at the equivalence point, all we have is H2O. Is H2O an acid or a base? Yeah, it's not a very strong one. But at the equivalence point, this reaction is how we determine the pH. What's the pH for this reaction? 7. Right? If I plug in the K at 10 to the minus 14th is equal to H0+ times OH minus, we solve for X, we're going to get 10 to the minus 7th. Negative log of 10 to the minus 7th is 7. So really, I could have had an even more complicated if-then statement that says, if they're both 0, then 7. Okay, so there should be a point right there. Okay. For a weak acid, strong base, it's a little bit different. Anna, tell us what that reaction is like.
For a weak acid solution and a strong when a strong base is added to a solution of a weak acid, a neutralization reaction occurs. Conjugate acid plus OH minus yields conjugate base plus H2O.
Wait, say that again? It says conjugate acid?
Yeah, conjugate acid plus OH minus.
It's not both of them weakest. It's mismatched.
So last semester I told you normally we think of a conjugate acid-base pair. We think of a weak acid and its conjugate base. They're calling them the pair. They're saying the conjugate acid and its conjugate base. Okay. So I'm just going to say, instead of that conjugate, I'm going to say weak acid, which we normally just put HA, right? As a generic weak acid. HA plus OH minus yields what?
H3O plus.
How am I going to get H3O plus?
H2O.
H2O, right? We don't have 3 hydrogens in here. So HA is going to donate its proton to the strongest base, which is now OH minus. We're going to get H2O. That's hence the term neutralization. And what's the other product? A minus. Now there's a problem with doing these calculations. It's not as simple as the strong acid, strong base, because we cannot assume that whatever we've put in of this, we cannot assume that 100% of them are going to actually donate. Actually, no, I just said it straight. We can assume that whatever's in here will donate its proton to OH minus. But what if we haven't completely used up all that HA? Can we just take the negative log of the excess of HA and get the pH from that? No. Whatever's left in this solution does not completely ionize. So once we do a limiting reactant problem here, we have to do another calculation. We have to set up the weak acid equilibrium. So once the hydroxide, if its hydroxide is limiting, this reaction will occur to completion. We could do this one like a normal limiting reactant problem. Okay, but once the hydroxide's gone, the HA is still going to donate protons to whoever it can. If the OH minus is gone, the next strongest base in solution will be H2O. So it's going to donate them to H2O, forming H3O plus and A minus. So essentially, for doing weak, strong calculations, we first have to do a limiting reactant problem, then we have to do an equilibrium problem. It's a two-step process. Okay? So, I'm going to do this calculation for a few very important points on a titration curve. Pick a weak acid. Anybody know any weak acids?
HCN.
Who?
HCN.
HCN. Ooh, that's a good one. Hydrocyanic. Ooh. Interesting. Okay. So we're going to do HCN. All right, the first point that I want to calculate is 0 milliliters. If we haven't added any NaOH at all, what is the pH of the solution? In other words, what pH does this titration start at?
The negative log of the weak acid.
No, it's not that simple.
It's not that simple. The weak acid does not completely dissociate or completely donate its proton. We got to actually plug into an ice table here. We got to say, okay, well, if we start with 0.05 molar HA, assume these start at 0. This is going to go down by X. This is going to go up by X, 0.05 minus X. X and X will be our equilibrium value. We know the Ka can be written as the concentration of the products over the concentration of the reactants. And to actually get an answer, we need a value of Ka. And I just Googled it. It's 6.2 times 10 to the minus 10. So we know how to do these. That's our K value. We plug into our ice table values, x times x over 0.05 minus x. This is why you need your calculators out. Let's see if we can solve this. Would you make the window for it? This constrains your x. What's the biggest x can be?
0.05.
0.05, the min?
0.
0.
That's what I put.
Your y min?
6.2 times 10 to the negative 11.
Correct. Your max?
6.2 times 10 to the negative 9.
Yep.
I can't find it on mine.
Check your equation. You might have typed something wrong in your equation. I'll show you mine. So yeah, basically all you can see is that K value because the actual X that solves this is so small, your Q, the whole right side, is really squashed up against the Y-axis. So it almost looks like you can't see it at all.
I think it's just sometimes it doesn't show sign change.
Still trying to figure it out?
I still can't see it with my window. But
You should not be able to see the intersection because the actual solution is so much smaller than your X max. It's like crunched here right along this axis.
But when I can't
You don't
see
need to see it, you just need to get an answer.
But sometimes when I do intersection and I don't see it and I just click it like twice, it says like no sign change. Like
So if that happens, make your X max smaller, right? We know from this, we're not seeing this thing shoot up anywhere here, so it's gotta be really, really small. So maybe try 0.005 or 0.005 if you actually wanna see it. If you're not getting it, the other suggestion would be to take when it says guess and bring your guess closer to 0. Then it might be able to find it. Okay? Anybody not getting this?
I'm not. I just can't get that value.
So, second trade, intersect.
Oh, 3.
Yeah, because it wants to know what curves you're using, and then it wants you to get close to the answer, which is just to save it. It's lazy butt sometimes. Okay, so if that's our X, what's our pH? 5.25?
yeah.
Would you the negative log of this? Since this is our H0 plus concentration, the negative log of that should give us our pH. 5.5. Somebody confirm?
Yeah.
5.25? Okay. That's pretty high.
Hey, I thought you had to like find the Ka and then the negative log of the Ka. No?
The Ka is used to find the equilibrium concentrations. The equilibrium concentration of H3O plus is used to find the pH.
Okay.
That's starting out at a way higher pH than we had with our strong acid titration. Why? It's a very weak acid. Look at how small that K value is. Super weak. Not that great at a proton donor. So we shouldn't expect there to be a whole lot of H3O plus in solution, and so we shouldn't expect the pH to be very low like it would be for a strong acid. Okay? All right, let's try. Ooh, I'm missing something here. How much are we going to titrate? How many milliliters? Just give me a number. 100, thank you. Titration of 100 milliliters. Now, we didn't need that for the first calculation, but we're going to need it now. Because I'm going to say, all right, let's do 10. What will the pH be after we've added 10 milliliters of NaOH? Well, the first thing we have to do is to figure out, with the amounts we have, how many moles of each of these do we have? So, we have 100 milliliters of 0.05 molar HCN. How many moles is that? I'm going to change this to our actual substance. How many moles of HCN are we working with? How much? 0.005, right? 0.05 molar times 0.1 liters means we have 0.005 moles of this to start with. If we've added 10 milliliters of 0.1 molar NaOH, how many moles of NaOH have we added? Ten milliliters of 0.1 molar NaOH. How many moles are there? 0.001?
Yeah.
Yeah, because 10 milliliters is 0.01 liters. If we multiply that by 0.1 molar, we get another 0.001 moles of this. Okay? Who's limiting? OH minus. So, this is sort of interesting. You can actually do stoichiometry problems kind of like our ice table. Right? We know if this is our limiting reactant, we know this is going to go down to 0, right? It's going to go down by 0.001, which means this is going to go down by 0.001 moles as well, right? So we'll be left with, after the reaction, 0.004 moles of HCN, 0 moles of of OH minus. We don't care about H2O, but here's something interesting. Now we've actually formed from some CN minus, right? If these go down by 0.001, the CN minus goes up by 0.001. Okay? So after this reaction occurs, here's the amounts of things that will be left in solution. Anybody have a question about that? It looks a little bit different, but this is basically just stoichiometry. Now, what we really need is the molarity of these things. So what's our total volume right now? 110 milliliters. So we have to take each of these and divide by 0.110. Point what? 8036? 036. Okay, don't forget about Cn minus. We got 0.001 moles of that in 0.110 liters. That gives us 0.009 molar Cn minus. Everybody with me here?
So where'd you get that 0.112?
That is the total volume of solution. If we started with 100 milliliters of this HCN, now we're saying we've added just 10 milliliters of NaOH, so our total volume is 110 milliliters. That's an important thing to keep track of, that every one of these calculations we're going to have to divide by a different volume here, right? It's the total volume, the volume we started with, plus the volume we've added. Now that we know what's in there, now we have to realize that, well, HCN and Cn minus are subject to this equilibrium up here. And now we have to update our values. What do we have? Well, we have 0.036 molar HCN, but we have 0.009 molar Cn minus. That's important. We have to keep track of the fact that now there's still some Cn minus in the solution. Okay, that's going to affect our answer. H3O plus we're still going to assume is 0 for right now. And we're still going to go minus x, but now we have 0.036 minus x here, x for the H3O plus, and 0.009 plus x for the Cn minus. So we're going to be a little bit nastier of a equation. That's why we use the graphing function. So, let's see, we're going to do x times 0.009 plus x divided by 0.036 minus x. My window, I suppose we can drop this down to 0.036. The k is still fine, so we graph it. Find the intersection. 2.48 times 10 to the minus 9. Now we take the negative log of that. We get 8.6. Somebody confirm that?
Yeah.
8.6. Wow!
That's basic.
That's basic. Times 10 to the negative 9? Yeah. You don't like my 9? Okay. Did you got the same answer? Okay. So we've jumped up to 8.6. Okay. Now again, that's actually because we have a really, really weak acid, and the weaker the acid, the stronger its conjugate base. So now that we're producing Cn minus, and we have Cn minus in solution, Cn minus is actually really affecting this pH, and we're getting a pH of 8.6. Okay? So here's what I'd like you guys to do. I want to keep going with this curve. So I want these two columns to calculate the pH when 50 milliliters have been added. I want you guys, plus Mia, to calculate when 100 milliliters have been added. I want you guys to calculate it when 150 milliliters have been added.
Wait, what's the middle two column doing?
100 milliliters.
What's the similarity of any other to them?
Let's do it. Like 9 miles away and pulled behind me yesterday. Yep, you got me first, then you can do that. Well, this is the total volume, right? But how'd you get this? No, because now we got to the different amount of information. So we still have to do this sort of calculation. We still started with this much HC, but we got to figure out which one we should minus it at this point before we figure out what it is. So if we got 50 milliliters of molar pH, mole soluble. So if we know the molarity from points, we plug it in for the
You
bigger.
already did it? So I'm trying to think, you had 7.6 pH. That makes sense.
Equals. We don't know how many moles, that's what we're trying to find.
These are the MC over.
And that's the liters.
I think it would MC it. Let me see your signal.
But is that liters? Oh my gosh. Well, I gave you guys terrible numbers. Yeah, I did it backwards. Crap.
I got an answer, but I just did the negative log of the OH concentration that I got in excess.
Yeah, okay, I'm sorry. I did the mental math wrong. I want you guys to do 20 milliliters added. You guys do 30 milliliters added. You guys do 40 milliliters added.
How much are we doing here?
20, 30, 40. Now, when we look at our reaction, we have 0.005 moles of our acid, 0.002 moles of OH minus. Who's limited? OH minus. So we know that one's going to go down to 0. So it's going to go down by 0.002. This is going to go down by 0.002. This will go up by 0.002. So figure out how much is left, and then divide by your total volume. Anybody struggling? Everybody stuck?
I have one question with the size table. So I think the first step of the reacting is 300 years I got.
Good.
The concentration, what do I do for CN minus? How do I find?
Well, if we went down by this much NaOH, what did it turn into? Because it turned into water, the OH minus, right? But since there's a 1-to-1 ratio between the amount of hydroxide we use and the amount of CN minus we produce, we're going to produce this many moles of CN minus.
So
But don't forget to divide by your total volume. What did we get the last time? What's the negative log of 2.48 times 10 minus 9? 8.61. Let's see. Just as long as we're a little higher. Well, I could print it out for you, but I'm not 100% sure.
I guess we're doing the homework.
Probably more like Friday.
Friday we're at school.
Thursday.
You want 2 days from now?
Yeah, we'll see what I can get.
Impossible though.
It's not impossible.
I could do the first half page. And
Okay.
you finish it.
Wait, you're getting the same section?
Oh. It's gotta work.
2.51, maybe that's your problem. You have one more digit.
Give it a number.
So, this is 0.003 divided by,
Oh, you can do it later, Lord.
good. Cool. How we doing over there? Mia,
8.60.
What?
how you doing? What step are you on?
Oh, yeah.
No,
No, we have 30.
What?
That is the.
Dubstep?
No, I don't do it.
Okay. Well, look where I wrote the big one.
Is that Thursday?
Do you understand what I did there?
There's graphic things like that.
I don't know where to go.
What I'm doing, but it says there's no sign change on my intersection.
Did you listen to M2's question?
For what, window?
Yeah, M2. Because she literally asked
So,
right
for
after I
both of
finished
them,
the
there's no
calculation.
really close together.
No, just for the X one.
That's the total volume at that point. You have 100 milliliters to start with, that's what it says on the top of the graph. And then I said, let's calculate the pH, and we've added 10 milliliters of NaOH. So we started with 100, we've added 10, we have 110.
Yes.
Okay, so do you know how many moles of OH minus we've added?
That number?
No, because now we've added 40 milliliters. You were asked to, I guess you were in this group. You were supposed to do 30 milliliters. What would that number of OH minus be in 30 milliliters of hydroxide?
Of 0.13 liters.
But
But what, the mole status?
Now if you have more volume.
I know we don't.
I got this number.
I got 9.38.
That's the definition of molarity, right? We know we're titrating 0.1 molar NaOH, that's what it says on the x-axis, right? When we did the first calculation, the liters, we added 10 milliliters, that's 0.010 liters. When I solve for x, that's how we get the number of moles here. You're not adding 10 milliliters, you're doing it for 30. So you'd have 30 here, that's how you can get the number of moles of OH. This is still the same,
Yeah.
but you're gonna have a different number of moles of OH minus, so calculate that and then figure out what you're left with.
I got 9.38.
You got 8 point what? 8.60? 637?
8.6037.
So just about what we had last time.
I got 9.38.
9.38?
So 30 more.
You got what?
The thing I'm not sure about is
You
my,
got .603, you got .60.
I probably did because it looks like it's supposed to be.
Should be lower than theirs.
I got 9.38, but I'm just not sure about my intersection.
9.38 isn't right.
Because I know my intersection value, I don't feel like it's right.
Okay. Let's figure out what we're doing here.
Wait.
I'm worried about this middle one. You guys did 30?
Yeah.
So for 30, this should be .003, right?
Yeah.
So this is going down by .003, as is this. So we're left .002. .002 divided by 130 milliliters, or 0.13 liters. What's your concentration?
0.0154.
You agree? The initial concentration of HCN? Actually, you don't like that? Did you not change the volume? You divide by 0.11? Okay, so at this point, when we've added 30 milliliters, we added to the 100 we originally had. Okay, that should give us our concentration there. Now this goes up .003, so .003 divided by 130 milliliters gives us what?
0.023.
So now we have plus x.
That's what I did with my x value from graphing is wrong. It's broken. My calculator's broken.
Wait, what did you get?
Is that what you just got?
No sign change?
Yeah. That's why then I finally just like kept moving it around until I finally got something. That's why I don't know if it was right.
I got 4.15 times 10 to the negative 7.
Oh wait, I got it. I got something.
Didn't change my window.
I think I got the right intersection.
Wait, Steven, what did you get?
But I got 4.15 times 10 to the negative 10 for an intersection.
Yep, me too.
And that gets along
Now-
with 9.38.
Did you see what I did wrong?
What?
I didn't change my window.
Yeah.
This thing's some sort of uppy-downy. So my window went past that first up and calculated it down. All right?
I finally got it to show the actual intersection.
Yeah. So I did it by just changing my window here. And then it worked. Okay, so 4.15
That's gonna be
times.
a 9.38 pH. That's what I got before.
Okay.
So
Wait,
I
that's
was
at
right.
30?
So I was right.
No, that seems too. Yeah, maybe.
I got that too.
Just roll the windows.
Yeah, 9.38.
I was right all along.
Oh yeah, we were at 8.6, right?
Yeah.
So 9.38 is not that much higher.
You made me think I was wrong.
Okay. That's at 30?
You made me think I was a failure.
Oh my gosh, I apologize. 1,000 pardons. How dare I? I'm not sure if I like this number. Are we confident on that? Well, the two people are capable of making mistakes. What did Cransky
I'll
do?
do it and make sure they didn't get it wrong. I'll make sure Andy didn't make mistakes.
Plug it into your ice table. This is your initial for HCN. This is your initial. Oh, you did? Where's the graph?
Every time you say each
Graph
other
it?
face and then it
Oh, wait.
for OH, okay. I got
Well,
it.
What is your K expression? K expression is H3O plus. You have X, right?
All the speech is soft right
Did you
now.
get the final, like, OA thing?
What?
Times A minus, which you
I got
have
9.8.
something minus X, right? So graph X times this, sorry, plus X.
You didn't even have it right.
Yep. So this should be 0.09 plus X. Yep. So X times 0.09 plus X. Divided by.
That's just the worst graduation speech I've ever heard.
I don't know what she's talking about.
If that was our graduation speech, I wouldn't graduate. I would refuse my diploma.
Just leave.
How about the 40s?
It was awful.
Emily, what'd you get?
Awful. I hated them.
I got 9.81.
9.81. Anybody else get that?
Karina did.
I didn't know some people could be that bad at writing a speech.
Oh. Okay, yeah, our number's wrong, we're gonna fix it.
I told you they were wrong, Mr. Bull.
9.0 sounds more reasonable. Because that's gonna be kind of like, yeah.
Yeah.
Tina! Six them. Kransky got a different. .002 divided by.
Bro, like,
Those
why,
aren't the serious.
you know what I don't get, like, why are they always focusing on
like
personal life for graduation speech?
We're not gonna see
Yeah,
each other outside.
Yeah, like,
So.
Point zero.
I know a lot of them just make it really personal.
like, people made it about them, like, it's a graduation.
I would just
Yeah.
keep running it. Don't round yet. Okay. All right. So, what did we have originally? 5.25.
Yes.
Then we went up to 8.6, then 9.0,
9.38.
9.38,
9.81.
9.81. Okay, so if you're not getting those values, we got to figure out why. All right? So I'll kind of leave it up to you to do that because I want to show you how to do 50. 50 is going to be hard. At 50 milliliters of NaOH added, let's go back and look at this table over here. At 50 milliliters of NaOH added, that's the equivalence point.
Oh, snap.
7.
We've got equivalent number of moles of OH minus and HCN. So these are both going to go to 0. CN minus is going to go up 2.005 moles. And if it's 0.005 moles, what's our total volume right now? 150. 150.150. What's our concentration of CN minus? 0.03333. Okay? Now, here's the problem. What's the strongest acid in solution?
The water.
You said what? H2O? Good, I said HCN.
No.
Why is it not HCN?
There's no.
It's all gone, right? So our strongest acid is H2O. What's our strongest base in solution?
CN minus.
CN minus. CN minus is the conjugate base of a weak acid, so it's a stronger base than water, okay? So we can't actually do this, we can't use this table right now. Can anybody see why?
We don't have any HCN.
If we have 0 of this and 0.0333 of this, how can we go up from this 0 and up from this 0, right? So this no longer applies because we don't have any HCN.
You H2O
So,
plus CN minus.
what we need to do now, since our strongest base in solution is CN minus, we have to say what does CN minus do? Well, we said that's our strongest base, and our strongest acid is water, so those are going to react, and what do they form?
HCN again?
HCN
And OH.
and OH minus.
That's wild.
Now we know that this is starting out at 0.0333 molar. We don't care about water. These we're now assuming start out at 0. But now we're going to form some of them as the CN minus starts grabbing those protons off of water. Now, here's another tricky thing. You agree that this is the equilibrium constant expression for the reaction I just wrote?
I do.
Is that KB, not KA?
That's Kb. Don't be calling this Ka. This thing is not behaving like an acid. It's a base. Where are we going to get our Kb value?
KA value.
From the Ka here. We know that Ka times Kb is Kw, so Kw over Ka should equal our Kb. So 10 to the minus 14th over 6.2 times 10 to the minus 10th. What's that?
1.61 times 10 to the negative 4th.
And now that's equal to x times x over 0.0333 minus x
No sign.
Yeah.
We got a number?
0.0.
Faster than me.
And I did it by graph.
Thank you. Point what?
002.
Don't you be rounding that too? How dare you? That's 10% rounding error. We don't round till the end. You want to round on the pH? Fine. Don't round here. What else?
370419.
Okay. All right, that's okay. Now take the negative log of that. 2.6. It dropped.
Subtract from 14.
Subtract from 14. That'll give you the POH. Right? So 14 minus 2 point, what she said? 11.845. 11.349. Okay, so now we're starting to get a jump in our pH again. Okay, now what about 60? What do we do at 60 milliliters added? Oh, there's so much work. Okay, I'm going to switch these boards real quick.
This is
This is wearing too deep.
Okay, who's our limiting reactant now?
The acid, the weak acid.
The weak acid. So we'll go down by 0.005. This will have 0.001 remaining.
Yes.
This will go up by 0.005 still. Okay, now it's 160 here. So what are we at?
0.3. 0.03.
Thank you.
I got close.
Get the number back.
Okay, so what we could do now is actually plug in. Where did it go? I switched them. I can plug this in. Oh wait, what's this? 0.001 divided by 0.160.
0.0065.
Is there more to 6 than this?
Yep.
How much more are we talking?
Well, the stuff we're going to do after this is very closely related to this, and once you really get good at solving these equilibrium problems, the other stuff's going to be easier. So let's power through this. We'll get there. Okay, so now we've got our ice table. Somebody's going to give me an answer. Come on, quadratic girl. Come on, graph boy.
That sounds like short girl.
Yeah.
Short boy and mom.
Sounded a little bad. I'm a graph boy.
That's so good.
Oh, yeah, this is still recording.
Guess we go bio.
AP chemistry test me.
It's the multi-single trackable.
Millie is 10 to the minus third.
Oh.
I kinda wanna think about it.
I'm ready for me. But nothing, I just we were done on this class.
Oh. I'm not-
7.11 times 10 to the minus 4?
Yes.
You need to slow down.
Can I make first?
Seven point zero six eight.
Stop! You know that's not what I meant.
7.068.
I'm still on the first ice table. I got behind.
Are you rounding or am I?
No, this is quadratic.
Oh! Right, because it's different somehow. Did I type something in differently? Oh, I typed in 0.315, not 3125. Come on, Bull.
Come on, Bull.
Come on, Bull! You're better than that. Have some respect. Now when I have to get the same answers that you got, I'm going to feel very silly. 7.06 times 10 to the minus 4. Okay, now, careful now. What's the POH?
So, okay, or negative one of that.
Oh, you have to add it to back to the 0.00625. Can you move so? Thank you.
Equilibrium concentration of hydroxide is 0.00625 plus this number, which is what? 0.00. What is it? 0.013?
What's X?
7.06 times 10 to the minus 4. Ah, 0.00695. Okay. 14 minus that.
11.84.
11.84.
How about that?
Okay. Now, here's the thing. Look at this solution. Look at the amount of hydroxide that was in there originally. 0.00625 molar, right? Look at how much the Cn minus added to that. Did it add a lot?
No.
Not much, about 10%, okay? But it really didn't contribute that much, okay? Most of the time when we do these, you can actually sort of ignore this calculation. This would be the way to find out the actual exact amount of hydroxide left here, but really, as a first approximation, normally what you can do is just figure out, okay, if this is my excess hydroxide, what's the POH? What's the negative log of 0.00625?
2.2.
2.204, 14 minus that,
11.795.
11.795. We got 11.84, so we would have got pretty darn close to this answer just factoring in the excess hydroxide and finding the POH from that. Okay? And actually, this is about the weakest acid we're going to have. So it is having about the strongest conjugate base we can possibly have. Almost any other calculation you're going to do with this is going to be pointless to actually do all this. The amount of OH added by your conjugate base, most of the time, is extremely small compared to the amount of excess OH already in the solution from the original titration. Okay? So you could do all this, but you can save yourself time by just approximating it. Negative log of the excess hydroxide gives us the POH, 14 minus that for the pH.
Where did you get the
625?
695?
Oh, when I found the X here, to actually know how much hydroxide is in there at equilibrium, we have to plug that X into this. This is the equilibrium amount of hydroxide. That's the thing that a lot of people forget.
Okay.
In the other calculations, we assumed it started out at 0, so that it just was X, but now it doesn't start out at 0.
Okay, so for that second step, do we need that ice table if it's that small of a difference when you add that X step?
So here's the thing. All right, let me talk a little bit more about the pH curve now. If I trace this out, this is the general shape. Okay. Now this is a pretty weird looking one because we have a very, very weak acid. Okay. I've done this. I used my fourth best friend. That same spreadsheet that I did the strong acid, strong base titration, I did a weak acid titration. This was much harder because now I had to calculate the amount of HA. I had to actually do a equilibrium expression calculation and figure out the pH. Okay, here's the curve I come up with. Okay, now this is a much weaker acid than we used, but what we see in general when we do a weak acid titration, first of all, we see a really sharp increase in pH at the very beginning. We didn't see that with the strong acid. It just sort of went. With a weak acid, we see a little bit of a spike, but then all of a sudden it levels out. It doesn't do that much. Then when we get very close to the equivalence point, then we start to increase the pH a lot, and then eventually we level off again. Okay? So each region of this curve has some significance. And each region of the curve, we have to calculate the pH in a slightly different way. At the very beginning, we just calculate the pH based on the weak acid equilibrium. Okay? We actually do that all the way up to the equivalence point. Use stoich, then weak acid equilibrium. We noticed when we did these calculations that from about 10 to 40, we were adding all this hydroxide. The pH only went up by 1.2 points. The pH barely changed for a good chunk of this calculation. This is what we call the buffering region. We're going to talk more about buffers this week, but this region right here, the pH is not changing that much. Buffers are substances that resist changes in their pH. So we've actually created a buffer here, and so the pH is not changing that much. Again, this point here, this point here, we call the equivalence point. How did we calculate the pH here? We had to do a conjugate base equilibrium problem. Right? That's the kinds of things I was doing here. How much conjugate base have we created, and then how much hydroxide is that going to produce? That allows us to calculate the pH. Okay, and then what I tried to say at the end here is anything past the equivalence point to a pretty good approximation, we can just use the concentration of hydroxide that's excess to find the POH, then use that to find the pH. If we know we're past the equivalence point, let's just figure out how much excess hydroxide is there. Let's find the concentration of that excess hydroxide, and let's just take the negative log of that. And we should get very darn close to the true answers, especially if it's a not super weak acid. Okay? Now there's one point here that I didn't calculate that I actually would like to. I don't have a lot of time. But 25 milliliters is a special point on this curve. What do you think the pH is approximately at 25 milliliters?
9.18.
9.2, 9.19, right? Somewhere between these two. Okay? There's a really easy way to find the pH at this point. pH is equal to the pKa. At this point, there's another equation on your equation sheet. Second from the bottom. The second from the bottom equation on your equation sheet says pH equals pKa plus the log of A minus over HA. Well, at this point, halfway to the equivalence point, we would have added 0.0025 moles of hydroxide. So what that'll mean is we'll have 0.0025 moles of this and 0.0025 moles of CN minus. So if these have the same amount of moles, they have the same concentration, right? So in the equation we just looked at, if pH equals pKa plus the log of, in this case, CN minus over HCN, if those concentrations are equal, this is the log of 1. What's the log of 1? 0. So at this point, pH equals pKa. How do we find pKa? Negative log of Ka. Let's take the negative log of Ka. 9.2. Okay, so this is a special point here we call the half equivalence point. At the half equivalence point, pH equals pKa. So it ends up being a pretty easy calculation. Actually, we can use this equation to get a pretty good approximation of the pH all along this buffering region. For the amounts that you guys did 20, 30, 40, look at your concentrations of HCN and CN minus that you used. Look at what you actually plugged into your ice table here. Divide those. Divide your concentration of CN minus by your concentration of HCN. Do it now. Kransky, you had 0.009, no, 0.016 and 0.025, was it? Divide those. Then once you get that ratio, take the log of it.
That's the exact same number. That's so convenient. So we don't actually have to go through all of that math, we can just use this equation. No?
Is everybody getting a number pretty close? We said the pKa was 9.207, so you should be taking 9.207 plus the log of whatever that ratio is that you had. And you will get very close to the same answer, okay? The thing is, this equation is a simplification. It's a simplification because essentially what it's doing is ignoring x. Right? If I take the negative log of both sides of this, I get negative log of Ka, pKa. Negative log of x, well, x is our H3O plus, so the negative log of this is actually our pH. Then we've got the negative log of this ratio. Okay, so basically when we do a little bit of math and rearrange it, this equation is the negative log of this equation. That's all it really is. Okay, but it ignores the plus x and the minus x here. Most cases that's going to be okay. We found the x here was 4.5 times 10 to the minus 10. Is that going to affect this?
No.
Not at all. Is it going to affect this? Not at all. Okay? So in most cases you can use this. The only time you can't is when the Ka starts to get reasonably large. Like if our Ka was 10 to the minus third, our x is not going to be negligible compared to these amounts. And we're not going to get the right answer. Okay? So I would caution you in using this equation too much because it really is just an approximation. As long as your K is small, it works great. But if your K gets to be larger than about 10 to the minus thirds, or if your concentrations start to get really small, that equation doesn't work. All right? So you can try it in your problem set when you're working on that. If you do the titration the long way, try it the short way and see how close your answers get. All right. Woo! That was a double already, Mia?
You didn't even get
Like about 10 minutes.